morning. The last class we have seen about amino acids, solution phase peptide synthesis, and necessity of protecting groups in peptide synthesis. And now we are going to see SPPS, that is solid phase peptide synthesis. We can consider the synthesis of a tripeptide alanine, valine, phenylalanine. And the free NH2 group is on the alanine, and the free COH group is on phenylalanine. And we have seen the solution phase peptide synthesis of this tripeptide. It contained, first coupling of alanine and valine, and then purification, and then deprotection, again the next coupling, purification. So it was a quite complicated procedure using solution phase peptide synthesis. Now we are going to see how simply we can do this tripeptide synthesis using solid phase peptide synthesis. The first step in the solid phase peptide synthesis is the immobilization of C-terminal amino acid to the solid support. Which is the C-terminal amino acid here? Phenylalanine. The phenylalanine contains free COH group. So you take the first amino acid, that is phenylalanine, in which the NH2 group is protected using BOC, tertiary butyloxycarbonate. And there is a free COH group. And you have, as the name implies, solid phase peptide synthesis. As the name implies, it contains a solid support. Normally, solid support is polystyrene based solid support. It's highly insoluble solid support. And in this solid support, in between these monomer units, the styrene units, some of these styrene units are functionalized with CH2Cl. So this polystyrene beads, the polystyrene polymer contains CH2Cl2 as active centers. So for simplicity, what we can do is we can consider this solid support inside a syringe, which is a fritted syringe, so that the solid support will not go out, only solution will go out. So that we can wash the solid support with a solution and then shake it and then we can push it out so that the solid support remains inside the syringe. So what we are going to do is, the first step is immobilization of phenylalanine, the N-protected phenylalanine. So you take the phenylalanine and a base in a solution. The solid support is already in the syringe. You take the solution inside the syringe, you shake. And what happens is, the COO minus will react with CH2Cl to form a CH2O-CO phenylalanine. That is, a new ester bond is formed. That is, the phenylalanine is attached to the solid support, immobilized to the solid support. So what you can take an excess of phenylalanine and weigh so that all CH2Cl is immobilized with the phenylalanine. The rest of the solution can be pushed out. You can wash the solid support, again push it out. So what is there inside the syringe? First it was solid support, simply solid support. Now the first amino acid, that is the phenylalanine, is immobilized. The first amino acid is there inside the solid support. So that is the first step. Now we will go to the next step. So in order to couple the next amino acid to this bottom, we know that there should be a free NH2 group. But our NH2 group of phenylalanine, which is already in the solid support, is protected with BOC. So we have to remove this BOC. And this we have already seen. Removal of BOC is with trifluoroacidic. Any acidic solution can remove the BOC. So normally we use 3% or 2% trifluoroacetic acid. So in acid solutions, an acid labile group, the BOC easily goes. So what we are going to do, we are going to take an acidic solution inside the syringe, you shake it and you push it out. Again, maybe we can do one more time to be sure that all bulk has gone. Again, you push it out, you wash it so that all bulk goes, and you have free NH2 group at the phenylalanine. So now the solid support contains phenylalanine, which has a free NH2 group. That is the second step. So the first step was the immobilization, and second step the deprotection of the NH2 group. Now we have a free NH2 group on the phenylalanine, which is ready for coupling with a new amino acid. So third step is coupling of bulk protected valine. So what we are going to do is we are going to take bulk protected valine in solution, which contains a coupling reagent, which is DCC, dicyclohexyl carbodiamide. We have seen the mechanism, we have seen the coupling mechanism and coupling reagents in the last class, so I'm not going to discuss the mechanism. So the solution contains the bulk protected valine. The NH2 group of the valine is protected with bulk and the coupling reagent. And your solid support containing the first amino acid, which is having a free NH2 group in the syringe. In the syringe, you are going to take the coupling solution which contains the bulk protected valine, which is having a free COH group, and the coupling reagent dicyclohexyl carbodiamide DCC. And you shake well. What happens? The coupling reaction takes place inside the syringe. The COOH of the bulk protected valine will react with the free NH2 group of the phenylalanine, which is immobilized on the solid support. So you get a dipeptide. The dipeptide is on the solid support, which contains a bulk protected terminal NH2 group. And after the reaction, you push out the solution from the syringe. You can wash this solid support, which contains the dipeptide, with DCM or any other solvent, and you push it out the solution so that you have the solid support which contains dipeptide, which contains phenylalanine and valine with a protected NH2 group. So we will go to the next step, the fourth step. For the next coupling, we need a free NH2 group. So our fourth step must be the deprotection of the bulk of the valine. Fourth step is the deprotection. So you take trifluoroacetic acid in the syringe, you shake well so that the bulk is deprotected. You push out the solution and wash the solid support again with some dichloromethane, and you push it out. So now the solid support after this deprotection step contains phenylalanine and valine, and then there is a free NH2 group ready for the next coupling. So now the free NH2 group of valine is ready for the next coupling. So the next step must be the coupling of bulk protected ALA with this valine. As I earlier said, you take the coupling solution which contains bulk protected ALA, which contains free COH group, and the coupling reagents which contains DCC in a solution. You take the solution into the syringe which contains phenylalanine, valine, dipeptide with free NH2 group. Or this NH2 group will react with the COH group of the alanine. After the coupling reaction, after you allow sufficient time for the coupling reaction, you push the solution outside, you wash the solid support, and again you push it out. Now your solid support contains the tripeptide, phenylalanine, valine, alanine, which is protected with NH2 group is protected with bulk. So almost your tripeptide is ready in the solid support. Now in the final step, you need the deprotection of the bulk and cleavage of the tripeptide from the solid support. So the final step is in a single step, that is final deprotection and cleavage of the tripeptide. In a single step, you treat with HF, which is a strong acid. In presence of acid, the BOC automatically cleaves out, and then the tripeptide is cleaved. The ester bond, which is the linkage between the tripeptide phenylalanine and the solid support, is cleaved with HF to have the free COH group and the solid support. So your tripeptide now is out of the solid support, now in solution. You push out the solution, don't throw it away the solution, because this solution contains our tripeptide, and then you evaporate and then you purify your tripeptide, and your tripeptide is ready. So the final step is deprotection and cleavage of peptide from the solid support. So from initial thing, the first step was immobilization of the first amino acid to the solid support. Next step is the deprotection of the first amino group to have the free NS2 group, and then coupling, and then again deprotection of the NS2 group, the deprotection of the BOC from the NS2 to have the free NS2 group, and then again coupling, and then again deprotection and coupling. So this process is very simple compared to solution phase peptide synthesis. Now already you can tell the advantages of the solid phase peptide synthesis compared to solution phase peptide synthesis. The first thing must be it is very easy to perform, because in solution phase peptide synthesis you have to do too many purification processes. In each step you have to do purification. Here you don't have to do purification, because you are taking it in solid support, you are pushing out the solution, and then you go for the next step of coupling, and then again you push it out, and then deprotection, coupling, everything in solid support. You don't have to do the purification step in each step. So the process is very simple. And again, in solution phase peptide synthesis, you cannot add too many equivalents to push the yield towards 100%. But in solid phase peptide synthesis, you can push the reaction towards 100% yield by adding too many equivalents of reagents, because purification is not a problem in solid phase peptide synthesis. So yield is high in solid phase peptide synthesis. And the last thing, it can be automated very easily. I explained this one with the use of a syringe, by taking an example, by taking the solid support in a syringe. That means this can be easily automated. Now many peptide synthesizers are available in market. So nowadays peptide synthesis is performed with machines, peptide synthesizers.